All right, guys, I wanted to try to do a little bit of review with you on springs. The first thing that's important is to realize that these show up in all sorts of different types of problems. So it's not just going to be simple harmonic motion. We're going to see these also in conservation of energy, F net equals 0, conservation of momentum, and simple harmonic motion. All right, so the first one, an ideal spring obeys Hooke's law, a mass of 0.5 kilograms, suspended vertically from the spring, stretches the spring 0.075 meters. The value of the force constant for the spring is most nearly. I'm going to identify this as an F net equals 0 problem. And in this F net equals 0 problem, we have the spring force that is pulling it up. We have the weight that is pulling it down. These are balanced forces, so our spring force constant is going to be the weight divided by how far it stretches. So I have 5 newtons divided by 0.05 kilograms, which is about 66. All right, next one. Two pucks are attached by a stretched spring, are initially held at rest on a frictionless surface as shown above. The pucks are then released simultaneously. If puck 1 has 3 times the mass of puck 2, which the defined quantity is the same for both pucks as the spring pulls the 2 pucks towards each other. So try to think about what type of problem this is. All right, so I'm going to identify this as a conservation of momentum problem. So my initial momentum and my final momentum, and for that sake, momentum all the time, has to be equal. They're always going to be equal to 0. So when they're coming back, the momentum of puck 1 going this way and the momentum of puck 2 going that way have to be equal in magnitude in order to cancel out. Third one, when a mass is attached to a spring, the period of oscillation is approximately 2 seconds. When the mass attached to the spring is doubled, the period of oscillation is most nearly. I'm going to identify this as simple harmonic motion. I don't have to move my equation around because it's already in the form of the answer. I'm going to put in ones for things that don't change, and then change the others by the factor that they do. And so I said that it's going to change by a factor of radical 2, and 2 times radical 2 is most nearly 2.8. Oh, wrong way. A block oscillates without friction on the end of a spring as shown above. The minimum and maximum lengths of the spring as it oscillates respectively x min and x max. The graphs below can represent quantities associated with the oscillations as a function of the length of the spring. Which graph can represent the total mechanical energy of the block spring system as a function of x? So I'm going to identify this as a conservation of mechanical energy problem because they're telling us that it is going without friction. And that tells me that at all points, my mechanical energy is constant. Which graph can represent the kinetic energy of the block as a function of x? I know that this maximum is going to happen when my spring force is at a minimum. This is going to be when x is 0. So it's either C or D. And then the question is, will it be parabolic or linear? And because the spring is proportional to x squared and not x, it's going to be parabolic. When an object oscillates in simple harmonic motion, its maximum displacement from the equilibrium position, which of the following is true of the values of its speed and magnitude of restoring force? So we have that when it gets to a maximum, it's going to change position. In order to do that, it's going to have a speed of 0. And when it's at the maximum, whether it's A or negative A, that's as big as the magnitude of this number gets. So we have a maximum for the restoring force, and 0 is our speed. A particle oscillates up and down in simple harmonic motion. Its height y is a function of time as shown in the diagram above. At what time does the particle achieve its maximum positive acceleration? So again, to get a positive acceleration, I need this negative term here to become positive. This is going to happen anytime we're below the 0, and this is going to happen when we're at the negative of the amplitude, which happens at 1 second on our graph. And then finally, the graph above represents the potential energy as a function of displacement for an object on the end of a spring oscillating in simple harmonic motion, which the following graph represents the kinetic energy of an object as a function of displacement. So if our potential energy is this parabola, our kinetic energy needs to match it.